10 minutes later, you're ready for low power service.
Okay. Now, can we put this in my pocket? Can you hear me?
Yes.
Oh, that's too bad. All right. First, I have some flyers and I can't reach you all.
Lettering.
I'm going to try doing that to my class.
Yeah.
Is that airmail?
This is airmail. Don't leave any.
Thank you.
Well, I should avoid standing in front of that, huh? Well, I suppose I'm supposed to talk about sidewalk astronomy. Am I talking too loudly? Can you hear me back there? Okay. I can stand in the fire pit, huh? Okay. Well, I suppose the first thing I should say is that the sidewalk astronomers are astronomical entertainers by appointment to Her Majesty, the American public. But, you see, the notion of amateurs getting their telescopes out for the public has spread worldwide. I have an awful racket here. Do you guys hear all that stuff? Oh, it's the wind. On this?
That's better now. That's better.
Go ahead. Is that better? Oh, boy. Anyway, so we used to call ourselves the San Francisco sidewalk astronomers. We don't do that anymore because although we started in San Francisco, we spread all over the world. And my view is that if the amateurs do not take the problem of getting telescopes out for the public will never have a chance to see what the universe looks like. It has to be when I talk that it does that. Farther from my... Is that better? Ooh, can you still hear it? All right. It's a real annoyance to me to hear it back over there. Anyway, I would kind of like to have you people ask me questions, but sometimes people ask me, how did the sidewalk astronomers get started? And that's because Bruce Sams, we used to call him Brucey, but he's now big enough to splash me against the wall. So nobody calls him Brucey anymore, but when he was 9 years old and up to my nipples, he had a 12-inch telescope, 7.5 feet long, and that was a bigger telescope than any telescope in the San Francisco Amateur Club. And he was 5 years too young to join their club. He was 9, they would let him in when he's 14. And he had a bigger telescope than any of theirs, and he's taken the astronomy class at the Academy. He's taken the astronomy class at the Academy of Sciences twice already, and his mother called me up and said that he needs somebody to talk to about telescopes and about astronomy, and she told me all these other things. And so I sent another boy over to his house to establish a club, and they insisted that I should be the third member. So there were 3 of us in 1968, 13 in 69, 30 in 70, and like that it went. Anyway, now we're scattered all over the world, so we've dropped the term San Francisco off of our name, and right now our secretary is in Southern California. If you want to know where any of us will be, call the 310 number. The 310 number is Pam Reed, and she's the secretary of the Sidewalk Astronomers. She lives in Whittier, east of LA. And I don't know where I'll be. If I want to know where I'll be, I call the 310 number. But from here, I think I go back to LA, to Hollywood, on the 26th, and then I have to drive up to San Francisco, and then I'm off to South Carolina and Georgia. Anyway, somebody once asked me when I was going into the visitor center in Death Valley to give the slideshow, somebody asked me, what's the connection between you and the Rangers? Well, I said, it's just that we do the same thing. The rangers we entertain the visitors with telescopes, and the rangers entertain them with parks. Now, one time when we were in Death Valley with a 24-incher, two 18-inchers, a 16-incher, and some smaller stuff, one young man said to me that if we go to an observatory, we get to look through a single telescope at a single object, and that's the end of the evening. If we find you in Death Valley, you have 9 telescopes on 9 different objects, and if we want to see anything else, we have only to ask. And I said, damn it all, he's put it in words. Now I need to say one thing about why we run these stupid things that are called Dobsonian telescopes. First of all, I should complain, I did not do that. I am the one who made fun for years, for 2 decades, I made fun of calling telescopes by people's names. I used to say, Cassegrain, Schmassegrain, Maksutov, Schmaksutov, Schmidt, Schmidt. Anyway, of all the people who live on this planet who should not have had their names attached to a telescope, I'm at the top of the list. Anyway, they just go like cannons. I was given an award in the East Bay Astronomical Society years ago, and when they give you an award, they sweet-talk you in front of God and everyone. And he kept referring to the Dobsonian Revolution, the Dobsonian Revolution. So when I got up, I said, all the previous revolutions were run with the cannons on Dobsonian mounts. But these are sensory cannons. They don't throw anything out. Anyway, the people who live in this world need to understand the world in which they live. And you have to convey information with your telescopes. It's not just seeing things. People meet us in the national parks. Many people have told us this. Finding you in the national parks with these telescopes is the highlight of our summer trip. And then they tell us that it's not just the telescopes, it's the slideshows you give first. And some have said it's not even the slideshows, it's the talk on relativity and quantum mechanics that you do in the slideshows. People have to understand why they're here, how they're here, where they're here. All those things people have to understand. Now, it's not true that everybody is very anxious to understand all these things, but some are, and those are the people that make it worthwhile. Now, I think you people should quiz me. I like to answer questions. If information comes in answer to a question, we have some use for it. If it doesn't answer a question, we have another ear to let it out. You must have noticed. Yes.
If we want to do programs, say for a park or for any kind of an institution or anything, like a sidewalk, astronomers, how do we do that?
All right. She wants to know, how do you do programs like this? I need to say some things about that. We have run quite a few years. With a 24-incher, we've run 80,000 miles through the national parks, through the Indian reservations, through the state parks, down to Mexico and up to Canada. But there are some difficulties that you run into. First, you have to make arrangements with the rangers in the national parks. So I have to tell you some stories. They're fairly ugly. Yellowstone didn't want us. Don't come. So we just drove through. Didn't get the telescopes out. At Rocky Mountain National Park, we were told that there are 2 places where we could set up the telescopes. Either at Hidden Valley or at a visitor center at 11,000 feet. Ooh, Baba. So when we got there, we found that our vehicle parking place is right behind an amphitheater. And there's flat ground there, no trees, and there are going to be people there. And so we asked, can't we just get the telescope out right there? Oh, no, you might attract a crowd. We're allowed Hidden Valley because the public is locked out. We're allowed this visitor center at 11,000 feet because no one's there after 6 o'clock. So we pushed, but we first of all fled to the YMCA. The YMCA has 3,000 people a day. 2,000 people a day look through the sun telescope. But we fled right away to the YMCA with those big telescopes. But we pushed, and we pushed at the national park. Finally, the naturalist said that there's a ranger going to give an astronomy talk at such and such a place on Wednesday. You can go there if you like, and after she is through, you can ask if it's all right to set up the telescopes. So we went, and we listened to what she said. I hope she's in this audience. 8 or 9 out of 10 things that she said were wrong. I really hope she's here because I owe her something. No, not because of that. You'll hear it. In just a moment, you'll hear it. So we listened, and when she was through, we asked her if it's all right to put up the telescopes. Well, she was furious. She said, they have no business to do this to me. I'm 19 years old. I have never studied astronomy for 5 minutes. They have no business to do this to me. I told you they're ugly. Anyway, the next day, she talked to the people for 5 or 10 minutes and flushed them down the tubes. Anyway, but at the YMCA, we had many people looking through the telescopes. We set the 24 and the 18 and stuff up over there. And they said if we had known you were coming, we would have put you up in buildings and we'd have given you the auditorium for your slideshows. Anyway, we have some other stories about the national parks. We used to go to Yosemite. When our 24-incher was first finished, I said to Brian Rhodes that Glacier Point in Yosemite must be the best place in the whole world for a public telescope, but there's that damned hotel. Anyway, we took it up there anyway, and we found out that the hotel has just burned down. Thank you. And I met a young lady there. She said, I was in the hotel when it burned down. I said, we're very happy to have met you. Anyway, so we have had the 24-incher at Glacier Point for more than 100 nights in the course of 12 years. And the seeing conditions there are the best that we have tested. You cannot test a this thing's still making that awful noise. Can you still hear it? Well, if you can still... Can you fix it out here? Is that okay? All right. I've never been wired in this particular way. Anyway, the seeing conditions at Glacier Point are extremely good. It's very quiet, and it's warm at night, and it's very transparent. Anyway, but right now I think it's considered a day use area, so not a lot of people there. But we used to get 300 people there looking through the telescopes, and we give a slideshow first. In the national parks, almost always, we give a slideshow first before we flush them down the tubes, because you cannot convey all that information at the eyepiece. You can't do it. If you can talk to them first, then when you get them out under the telescopes, you see, or looking into the telescopes, I climb the ladder, the 12-foot ladder, and I make an announcement, say this one's on M13, that's a globular cluster, and tell them something about it. The stars are 17 billion years old, made of nice clean hydrogen and helium and so forth. And I'll tell them the little one, that's the 18-incher, is on, say, the Ring Nebula. It's a gaseous envelope around an old star. Don't use the word planetary. It is meaningless. I know that's one thing I'm against Herschel, and that's about the only thing I get against Herschel. But it's okay for astronomers to talk that language, but don't use it in public. And the same with open clusters. What does that mean? And these astronomers talk about umbras and penumbras on the sun, shadows on the sun. It's hopeless for the American public or anybody else's public. You have to convey information. If you're going to do sidewalk astronomy, you have to convey information to these people. And you have to talk to them in their own language, not in astronomers' language. They don't understand that kind of stuff. Well, anyway, how'd I get onto all that? Anyway, we've been to Glacier Point a lot, but we don't go there now. Because the man who's there now, he's from Griffith Park, Dave Balow, he wants help with his Friday and Saturday evening programs, I understand, and he invites the amateurs, 1 week one club, 1 week another club, like that. But I understand the telescopes have to be taken down at midnight. We're not going to run to Glacier Point with a 24-incher and take it down at midnight. Not going to do that. Anyway, we used to sit there for 2 weeks at a stretch. Every night for 2 weeks at a stretch. We give a slideshow and run them down the tubes. But Dave Carricker was there. He was the chief naturalist years ago. He said that the Johns on that concave hill are going to have to go anyway. Put an amphitheater in there on that concave hill. And then you'll give a slideshow there. The ranger will give a sunset talk out at the point. Then we'll bring them in here. You give a slideshow against those dark trees. And then we'll send the people down along a path with various telescopes on various objects, and then put the 24-incher down in the hotel basement. That is to say, where the basement used to be. We never met him again. Now, he had another thing figured out in the right way. He said that if we put telescopes in the national parks, we'll have to procure the telescopes. We'll have to house the telescopes. We'll have to train somebody to run the telescopes. We'll have to pay somebody to run the telescopes. He says there's no use. He says if we leave the slideshows and the telescopes and the know-how with the sidewalk astronomers, we could get you from park to park for $5 grand a year. Never met him again. Sorry about that. But there are these sad stories. Now I have to tell one about the Grand Canyon. One of the rangers in Death Valley, Bill Clark was his name, he saw that what we're doing is ranger business. What we're doing is ranger service, ranger's duties. So he made us all come in and sign out papers and made us all unpaid employees of the Death Valley National Monument. And then he wrote to me, they've moved me to the Grand Canyon, come. So we packed and went to the Grand Canyon. The very first day we were there, I was told that I have to talk to the man who's in charge of building buildings, where to put an observatory. Well, I was too tired. I said, you have to wait till tomorrow. At any rate, that's really not the way to do it. The way to do it is to have the amateurs do it and not put an observatory there. But at any rate, we went there year after year for quite a number of years, and in 80, I think it was in 80, the ranger asked us to keep track of how many people used the equipment. And in 16 days and nights, it was 20,000 people. 20,000 people in 16 days and nights. Now the next year, which was 81, the naturalist sent me a letter, which he had Xeroxed, a letter sent to him, and I quote the first line, "We don't need to be exposed to such controversial views in the national parks." And in that letter, he put all his pet peeves against the scientists into my mouth, things which I never say, things which aren't remotely true. Anyway, he asked us not to return. Sent me that letter and asked us not to return. I stayed away for 14 years. Last year I went back as a guest of someone else. But I answered his letter. I said, we don't say those things. And you also don't say that the rocks at the bottom of this canyon started on October 23rd, 4004 BC. You don't talk like that. Why should we? Well, anyway, we should do these things in the national parks if there's any way we can do it, because that's where the American public collides with the sky. Now, I had a beautiful letter from France years ago that we're following your exploits in the magazines, but we don't just follow, we try to do likewise. They have a Coulter 17.5-incher which they use for the public. But he says, you set your telescopes there in places that make us dream here. Anyway, people in Belgium ask, can we use the term sidewalk astronomers? Of course you can. And people in the Philippines, can we use the term sidewalk astronomers? They have a logo with a sidewalk. The sidewalk and the telescope on the sidewalk. Anyway, now you can ask me some questions. That was all in answer to your question. Some questions are little with big answers. Who wants to ask? You can ask anything you like. Yes. I can't even hear you, let alone the rest of them.
What do you find is most useful in getting the children in?
Telescopes. What was that? That's the long and the short of it? Yes, telescopes. Because you see, most people, well, let me put it this way. There's a reason why we sidewalk astronomers run around with telescopes like this. Almost everything you see on the surface of this planet, your interpretation of it is colored by your genetic programming. It tells you how to interpret beaches, oceans, palm trees, grasses, suns, moons, everything, people, dogs, lions, everything. You've got a genetic programming that tells you how to interpret it. And when you look through the telescope, they shut up. Your genetic programming has nothing to say about the rings of Saturn or what the moon looks like through a telescope. Some lady at Griffith Park a few years ago said to me, we had Venus in the evening sky, a nice crescent Venus. She said, Venus looks like the moon, and the moon looks like the Earth, as if it was all my fault.
How much solar observing do you do with the Dobson telescopes in the daytime?
We do a great deal, and we always look at the sun in the daytime. I know. You left the door open. We make what we call fail-safe sun telescopes. We have suppose the tube is like this. We have a front plate at 45 degrees. It throws 95% of the light away. It's a transparent mirror, reflective 95%, transmissive 5. 5% of the light comes in. The objective is unsilvered. 96% goes on through. 4% comes back. So we're down to 1 part in 500. Hits the front plate, reflected up through a welder's glass. That eats 99%. Lets through only the green. Takes out all the ultraviolet, all the infrared, lets only about maybe 5/1000ths of the incoming, no, let me see, about 10 millionths of the incoming beam get into your eye, and that only in the green. And these things are fail-safe, because if the front plate is broken, the observer would be looking at the ground through a welder's glass. That's known to be safe. The only way you can burn your eye with a sidewalk astronomer's sun telescope is set fire to the telescope and hold your eye over it. First, you have to get permission. Somebody else back there, yeah.
Yeah, do you remember
The view?
Yeah, do you remember the view that just put you in?
That started on me? Yes, I do. First of all, I was in the monstery, you see. We call it a monstery. We wanted, and I was interested in galaxies. And we had a friend who had jaundice, and he had a glass disc on his table. I remember when we took care of him, he had this glass disc on his table. So we called him up and asked, how would you like to have that ground into a telescope mirror? Oh, he'd love it. Well, it turned out to be 12 inches in diameter and 1 inch thick. I had no idea. I thought it was much smaller. So that was the first one. We started like that. And when I first looked at the moon through one of those old 12-inchers, the third quarter moon, I thought, it looks as though you're coming in for a landing. I had no idea it looked like that. No idea at all. And I thought, my God, that's inside of me it thought, everybody's got to see this. That's what happened to me. And I don't know what's happened to you. Yeah.
I talked to you about 10 years ago on cosmology, and why don't you bring us up to speed on the undivided
Oh, you do you? Well, I'm much more interested in those things than I am in telescopes. I talk about telescopes under duress. And for the most part, the amateurs now know, don't make me talk about telescopes. So I'd be happy to talk about some of those things. And you know, I have a shirt on here. Can you read this? The Big Bang is a thing of the past. But nobody thinks it's the thing of the present. But you see, the Big Bang, I don't need this. The Big Bang people have this notion, you see, that about maybe 15 billion years ago, nothing made everything out of nothing. I don't think it will wash. I was talking to some little kids in Oregon about a summer ago, a summer before last summer, and I mentioned that the Big Bang people wanted us to believe that nothing made everything out of nothing. And one of those kids says, you can't make anything out of nothing. And anyway, so the problem is, the Big Bang people, well, let me tell you a story. I was at the summer scientific meeting of the Astronomical Society of the Pacific in Pomona in Southern California, maybe more than half a dozen years ago. And on the airplane on the way down there, I was from Northern California, I was thinking, you see, that the Big Bang people take non-existence for granted. They want to get the universe out of non-existence. I don't think that's possible. I have a button here that says nothing doesn't exist. Anyway, so I thought there is this problem. And so I was going to ask this question to William Kaufman, but Alan Sandage, who used to run Palomar and took over after Hubble, he gave a very nice 2-hour talk on the Hubble constant. He said, I want it to be 42. He says, so the Big Bang can go. I want it to go. At any rate, he gave a very nice 2-hour talk on the Big Bang, and all the way through, he referred to the Big Bang as the creation event. So at the end, I got up and asked, since we're now willing to talk creation event, and I wiggled my fingers like this, why must we assume that in the absence of the universe and in the absence of space and time, there would be nothing? Isn't it unwarranted? To me, it's warranted that in the absence of time, we have the absence of change. That's warranted. And in the absence of space, we have the absence of dividedness and the absence of smallness. Dividedness and smallness are space problems. Change is a time problem. I said that leaves the possibility that behind what we see might be the changeless, the infinite, the undivided, which to me seems a long ways from nothing. That was the end of the conversation. He was not going to talk on it, and I wasn't going to hassle him. But years later, Hawking gave 3 lectures at the University of California in Berkeley. I got into the first 2. I couldn't even get into the third. I couldn't get near enough to the campus to park my vehicle. When he first came out they gave him the Wheeler Auditorium, that's 750 seats. It was filled up right away. And the people that got to the overflow did it on the run. The next time, they gave him a 1,200-seat auditorium, and all the others for overflow, and they were all filled up. The third time, I couldn't even get near the campus, but I could see there must be at least 500 or 600 people out in the court who couldn't get into any of the buildings. Anyway, the first lecture, he wasn't going to take questions, but I got to had the opportunity to ask him a question outside after the lecture. So I'm to ask him a question answerable by yes or no. So he's in his wheelchair out in the sun, and I'm down on my knees, and it was very, very sweet. He's doubled over in his wheelchair with his hand on his machine. When he first came out on the platform, he said that whereas formerly he couldn't talk, now they made him this machine, and it was made in what do you call that? Oh, down this peninsula from San Francisco. Anyway, a little ways, Mountain View, down the peninsula from San Francisco. So he got a big hand because it was made in Mountain View. Then he said, the difficulty is that it gives me an American accent. Then he got clapter. Anyway, so I told him, I was very apologetic. I told him that in order that my question could be answerable by yes or no, my question will be lengthy. And I told him that whole story about Alan Sandage and myself. And I asked him, do you see any observational evidence on one side or the other, whether behind what we see might be a zero, or whether it might be the changeless, the infinite, the undivided? He took the trouble to have his machine answer me, I'm not sure it's a meaningful question. That's his way of saying no. If he saw the evidence, he would have said yes. He doesn't see the evidence, so he answers politely. But I see the evidence. Gravity is the evidence that the undivided is behind what we see. The electrical charge on the itsy-bitsy particles is the observational evidence that the infinite is behind what we see. And inertia is the evidence that behind what we see is the changeless. They all show in what we see. Now, it would be one thing if they had some other explanation for these things at Caltech, but they don't. The reason we send you all to high school before we let you go to the universities is so that you will all be polite. And none of you will ask the professors why the books fell to the floor. The professor has no idea why books fall to the floor and does not want to be quizzed on it. Now, Richard Feynman is very careful. After telling him what we do know, he tells what we don't know. That we know how matter behaves under the influence of inertia. We do not know why it shows inertia. We know how it falls in a gravitational field. We do not know why matter shows gravity. And as Einstein said, we cannot understand on theoretical grounds, we cannot comprehend on theoretical grounds why matter should appear as discrete electrical particles. Why do the itsy-bitsy particles have to be electrical? Why do the moving bicycles have to coast? And why do things have to fall? That's what I think is the changeless, the infinite, the undivided showing through. It shows in us also. We have a department of the government. You see, the changelessness shows through. Our yearning for the changeless shows through. We're after peace and security. As I said, we have a department of the government. And the infinite shows through. We run after freedom. And the undivided shows through. We run after love. But you see, the genetic programming pulls the wool over our eyes and has us run after these things in ways that get the genetic programming job done. But something happened to us that didn't happen to the chimps on the beaches of Africa a long time ago. Something happened to us that didn't happen to the chimps. And that's divided our genetic programming into 3 batches. A few million years ago on the beaches of Africa, we elongated our childhood. And if you elongate your childhood, you elongate your parenthood, okay? You can't have a long childhood without having a long parent. So we have these 3 batches of programming. We have a whole batch for being kids, a whole batch for being adult, and a whole batch for being parents. Now the prime directives of the genetic programming are twofold. Direct a stream of negative entropy upon yourself by eating and breathing, and pass on the genetic line. These are the prime directives of the genetic programming. Keep yourself alive and well by eating and breathing, and pass on the genetic line. Now, children don't do either one. Directing a stream of negative entropy upon ourselves and on our children falls on the parenting batch. Passing on the genetic line falls on the adult batch, and neither of them falls on the kids. So you see, we have this very interesting way of looking at this world. We can see the way, well, let me put it this way. I have a kid, he's 16 years old. He's got a few more days before he's 17. I told him a few years ago, all kids know that grown-ups are nuts. Watch it, it's going to happen to you. But we do have the opportunity, you see, and we all have the memory of it even after we get older. We all have the memory, at least to a certain extent, of how the universe looked like, how the universe looked before we got so stupid. You can laugh if you like. Yes? Any more questions? Have I said enough on that? All right, poke me. Let me say one thing, you see. I am not a Big Bang, enthusiast. Now, you know, in the astronomers, they, you know, we got in the astronomers. Let me tell you how that happened. They called me up in the spring. This thing is still doing that. Yes, but it does it when I talk. Can you still hear it? All right. All right. Okay. They called me up in the spring and said they wanted the sidewalk astronomers in a national park in September. I said the only national park we're going to be in this summer is Crater Lake, and it's the 2nd of July. Well, he said, we're not supposed to shoot till September. I said, tough shoes. So they got all their stuff together on a charter plane and flew it up to Medford and did all that first shooting in July. That was when one of the stars, when Saturn went in front of one of the stars, you know. We got to watch that through the telescopes at Crater Lake. Anyway, so that was shot up there. Now, in that movie, we're in there for decoration. We're the only people in the astronomers who are not professionals. We're there because we're the colorful people. We're there for decoration. And they didn't want any piece of information coming out of my mouth. So at Crater Lake, I'm about to pan the Big Bang, just about to pan it. And just when I introduce it, you must have heard of it. Cut. Anyway, that's how that happened. This hurts my ear too much. There. No. Whoops. Come on, fix it. Sorry. It's gotten to be too sore in here. You got to put it behind my ear or something. Stick it back there. Well, he was afraid if I use the handheld mic and get in front of that thing, it'll, you know what it does, it backfires. Anyway, I can hardly hear myself now. Where was I? Anyway, so they shot all that. What was I telling you all that about?
About the Big Bang.
Oh, yes. So it sounds as though I'm pushing the Big Bang. I never talk about the Big Bang except to abuse it. How many of you are willing to go along with the Big Bang? Let's have a show of hands. How many of you are still willing to go along with the Big Bang? Please put up your hands. How many of you are not? Please put up your hands. The rest of you are pure gold, yellow to the core. Well, none of us are sure. Oh, this still hurts. Can't you cut this spring down or something? Here, put a paper towel under there or something. All right, take it off and use that. Things. Yes, okay. Can you hear me still? This is quieter, isn't it? Oh. Anyway, you see, the Big Bang model can be compared, and has been compared, to a raisin pudding in the oven. And as the pudding gets bigger and bigger, the raisins get lonelier and lonelier. So that if you come too late for dinner, there may not be any raisins in your spoon. Now, there was another batch of people who thought that the universe might be more like a raisin pudding getting bigger and bigger in the oven, and the raisins getting lonelier and lonelier. But as the raisins got lonelier and lonelier, new raisins sprang up in between, so it don't make no never mind when you come for dinner. There are 5 or 6 raisins to a spoon. So those are the steady state people. But the Big Bang people didn't like it one bit. They said, where did you get those new raisins? And the steady state people said, where'd you get yours? Now, for some reason which I was never able to understand, the Big Bang people thought it's okay to get everything all at once, but not to get it little by gradually. Anyway, I don't see it quite that way. But I have a consideration, you see. When you consider what do we see when we look way out to the borders of this universe, first let me ask, how many of you think the universe is infinite? Please put up your hands. How many think it's finite? Please put up your hands. It's finite, you silly geese. The observable universe has a boundary about 15 billion light years away. We'll use an old number, about 15 billion light years away, because if there is anything beyond that, it's going too fast to be part of your universe. It's going so fast that radiation messages cannot come in, and since gravitational messages move the same way, they also can't come in, and the Canadian mail won't come in. So there's a border to the observable universe. Now, when we consider what happens to the material that we see way out at the border, what we see is that the radiation from there is gravely redshifted, approaching zero energy at the border. Now, if the radiation approaches zero energy at the border, so does the particle energy. But if the particle energy approaches zero at the border, so does the particle mass. From Einstein's 1905 equations, we know that if the energy goes to zero, the mass goes to zero, because E equals m. I know there's a c squared. I have to clean this up a little bit. Some of you know that equation is E equals mc squared, and you think the big thing is the c squared. The c squared is not in there. The c squared is to tell you how many ergs equals 1 gram. When we found out that what we call matter is just potential energy, then we had this difficulty. We have 2 units for it, the erg and the gram. Now, the gram is the energy of an atomic bomb. It's enough to vaporize Berkeley. The erg is the kinetic energy of a 2-gram beetle walking 1 centimeter per second. And c squared in those old units is 9 times 10 to the 20th. The speed of light is 3 times 10 to the 10th centimeters per second. We did the CGS system when I was a kid and when Einstein was also a kid. We did the CGS system, and the speed of light is 3 times 10 to the 10th. And the erg was the unit of energy, and the gram was the unit of mass. And when we found out that they're the same thing, we had to find out how many ergs equals 1 gram. So 3 times 10 to the 10th squared is 9 times 10 to the 20th. And what that equation tells you is that, carefully handled, the kinetic energy of 9 times 10 to the 20th, 2-gram beetles walking 1 centimeter per second would vaporize Berkeley. It's the last 9 digits that get you. Well, anyway, when you consider what happens out at the border, if the mass approaches zero, if the mass of the particles, as seen by us, if the mass of the particles approaching the border approaches zero, two very interesting consequences follow. We know that all radiation going through a field of low-mass particles gets so often picked up and re-radiated that it gets thermalized to 3K. Now, the amount of background radiation that we get by this model is the amount which we measure. The amount predicted by the Big Bang is about 2 orders of magnitude too high. I know they took it as their own thing when they discovered it in 1965, but it does not match the model. The amount we get is this amount if all the radiation is converted to the regular radiation is converted to 3K. That's the amount that we would get, and the Big Bang predicts about 100 times too much. The other interesting consequence is that out there at the border, if the mass of the particles approaches zero, so does their momentum. Is that part clear? The momentum is the mass times the velocity, and the velocity does not approach infinity. It approaches a constant. So if the mass approaches zero, the momentum approaches zero. If the momentum approaches zero, so does our uncertainty in the momentum approach zero. You can't have a big mistake over nothing. If the momentum approaches zero, our uncertainty in the momentum also approaches zero, and then by Heisenberg's uncertainty principle, our uncertainty in where the particles are approaches infinity. The particles are required to recycle from that border. They can't just go bebopping across it. They have to bebop back in. But they don't come in on the train. They tunnel back in. When an electron goes from one energy level in an atom to another energy level in an atom, it does not slide down the wall. It disappears in this energy level and reappears in this energy level. Electrons and protons are not things, and they do what things cannot do. They disappear in one energy level and reappear in another energy level, and it's called tunneling. And the particles at the border can recycle back in just by tunneling. These things are like dollars in the bank. If you write a check on a bank in Santa Barbara for a bank in Portland, nobody goes down and gets the stuff. It disappears in Santa Barbara and reappears in Portland. You must have noticed. So that's, see, in my model, that's the way it goes. We see a finite universe with a finite boundary, but the material from the boundary has to recycle back in. It gives the right amount of stuff recycling back in. It gives the right amount of background radiation. And it can go on indefinitely. Yes. I don't think they do anything special, but before Hawking thought they leaked, I also suggested that they leaked. It seems to me that if something falls very, very low in the gravitational field, deep into a gravitational well, so that the rest mass has to get very small, I have to clean some of this up for you. So the rest mass gets very small, then the momentum gets very small, and they can leak out through the uncertainty principle, the same as they get back in from the border. That's how I see it. I don't think that black holes can stay permanently as black holes. I think they have to leak, just the same as the border has to leak. Now let me tell you all something. If we drop something, let's say we have an old-fashioned marshmallow, an old-fashioned 10-gram marshmallow. If we drop it to a neutron star, we get 1 atom bomb's worth of energy in the splash. 1 gram comes out in the splash. Is that part clear to you? It's probably not, is it? All right, let's go back a little ways. Let's talk about watches. Let's say we have 2 identical spring-wound watches. One is wound up tight, One is unwound. They're both broken in exactly the same way, so they won't run. Which one is heavier? The wound up one is heavier because we put some extra energy in it, and energy is the only thing that's heavy. Now we're going to dissolve them in equal beakers of acid. What's the difference in the final solutions? One of them is warmer. Warmer means that the particles are moving faster. This time the extra weight is the weight of the kinetic energy. Energy is what's heavy, not something else. All right, now if we... All right, how do you wind up a cuckoo clock? Do you pull things down or pull them up? No, not both. You pull the weights up. You raise the center of gravity in the gravitational field to wind up a cuckoo clock. If you put it on a higher shelf, you've wound it up even more. Is that clear? All right. There's a reason why it's hard to walk uphill. You have to get heavier. Anyway, if we drop something to a neutron star, we get 1/10 of its rest energy out in this splash. If we drop it to a small black hole, the event horizon of a small black hole, we get 1/3 of its rest energy out in this splash. If you could put all the matter in the universe back together in a single black hole and drop your marshmallow in, you can get all of it out. The energy of an old-fashioned marshmallow is the energy of 10 atomic bombs. I know they'll sell you a big bag of them at the grocery store for $1.69. They don't know what the hell they're doing. Now the work you have to do to space the universe out the way it is 500 atom bombs per pound. 1 pound of anything, whether it's cow dung or whipped cream, is the energy of the St. Helens explosion. 1 pound of anything. We don't take it as seriously as it really is. Now it's also wound up by having the electrical particles so dinky. I learned that from Professor Lawrence at the University of California when I was a freshman in 1934. The work you have to do to push 2 electrons together makes them heavier together than they are apart. And if you had a great big electron and you made it smaller and smaller and smaller and smaller, down to the size of an electron, that's how much it would weigh. There's nobody else in there. That was the most shocking piece of information that hit me at the University of California. I always thought that matter consisted of these dirty little particles with electrical charge. No, there is just the electrical charge and the smallest the electrical charge, and there's nobody else at home. The universe is massive because it's spaced out against gravity and because it's spaced in against electricity. And it's the same 500 atom bombs per pound. You see things small by seeing them spaced out. You see them spaced out by seeing them small. You cannot break a cookie into bigger and bigger pieces. Now what else do I have to say? Yes. Somebody translate that. I can't hear it.
Antimatter. What about antimatter?
Oh, antimatter happens all the time, and it's no big deal. Because of cosmic ray bombardment, you have electron and an anti-electron made in your body about once in 2 seconds, I think. That's not a big thing. But you cannot make matter out of radiation. That's one of the troubles the old Big Bang people had. If the fireball is radiation, you cannot get matter out of it. You can get 50-50 matter and antimatter. And when they find each other, they go back to radiation. Out of radiation, you can get radiation. You cannot get matter. But there's still another difficulty, and that is that radiation doesn't exist. No response. You see, when I was at the university, we used to make fun of the professors. That on Monday, Wednesday, and Friday, they believe in the wave theory of light. And on Tuesdays, Thursdays, and Saturdays, they believe in the corpuscular theory of light. And on Sundays, they contemplate the problem in church. But you see, Einstein's 19.5 equations put space and time in as a pair of opposites in just such a way that the separation between the emission event and the absorption event of a single photon always goes to zero. We see the bright star Sirius 8.5 light years away by seeing it 8.5 years ago. And in Einstein's equations, the space separation comes in squared with a plus sign, and the time separation comes in squared with a minus sign. And if it's 8.5 squared minus 8.5 squared, you're left without change. The separation between the perceiver and the perceived goes always to zero. Now, we knew this about dreams. We've known it all along about dreams. When you wake up in the morning, you see that that space was in the dreamer. When you dream, you have a dream body, and there are other dream bodies in your dream, and the whole thing is in the space of your dream. But the whole dream, the space of the dream, and all those dream bodies are in the dreamer. What we did not know until 1905 was that in the waking state it's the same. The separation between the perceiver and the perceived has been always at zero. I know you will not find it easy to accept that. I've been working at it for 40 years. That's what the equations say, and that's what we check. We don't check the physicists' gut responses, we check the equations, and that's what the equations say. Now, I should very much like, you see, that everybody understands these equations of Einstein. The separation equation, the space and time come in as a pair of opposites, and that what we see as matter is just potential energy, and that they should understand Heisenberg's uncertainty principle. In my opinion, if you can't handle those three equations, you've thrown in your sponge. Now I think it must be time for me to quit, or I'll wear you all out. But if you want to ask me some more questions, have at it. Yes?
What do you call the Dobsonian telescope?
On the altazimuth telescope. However, I wrote a very nasty letter to Meade. I was up in Oregon, and they had a 16-incher up there with a great big ground board like this, about that big around. Guess how thick it was? 3/4 of an inch. Guess how many feet it had underneath? 9. Guess how come they can use all 9 feet? Because it's only 3/4 of an inch thick. Thank you. Anyway, I wrote them a real nasty letter. You can't run telescopes like that. I said, if you're going to bandy my name around, you owe me the courtesy to make something that works. They had 6 or 7 pieces of Teflon on the ground board around the edge on which the bottom board moved, and it takes quite a bit of a yank to get it to go around. I was disgusted, and they've got the tube painted white. None of you should paint your telescopes white. White paint is full of titanium dioxide, and it radiates feverishly in the infrared. We're not concerned about how these things handle visible light in the daytime. We use them at night. We have to know what they do in the infrared. And if NASA wants it to be black in the infrared, they paint it white with titanium dioxide and send it out there. Paint them any color, any dark color. Don't paint them any light color. What I call a Dobsonian telescope. You know, I didn't put my name on those things. We've had a name for them all along. But what happened was that in the 60s, the telescopes were only 4 inches and 6 inches, and they had to put, in order to see galaxies and things, they had to track them across the sky. So they were mostly on equatorial mounts, because they couldn't see the galaxies unless they took pictures, and then they saw them with their cone cells in the daytime. That's cheating. You never see galaxies with your cone cells. And your rod cells are stupid. In the daytime, you can see the leaves of the trees. At night, you can still see the trees. At night, your ladybird beetle cells go fast asleep, and you're left with your rod cells, which are stupid. So in order to see the galaxies, you have to have a big telescope and a great big image. Use high power, not low. You've got to use something like 15 powers per inch of aperture if you want to see those dim things. Don't go to low power like it says in the literature. I don't know how come the literature got written like that. Either those people don't look through their telescopes or nothing happens above their shoulders. Try it. What else? Am I dismissed?
I have a few questions.
Go ahead.
All right. You said that thing about NASA. If they wanted to appear black in the infrared, they paint it white?
Yes.
Well, then what's wrong with it being white?
We don't want our telescopes to be radiating in the infrared, because what they do at night is to exchange infrared with the night sky, and the night sky is a hell of a lot colder than the ground. And they exchange infrared with the ground, which is a hell of a lot hotter than the night sky.
You explained that to me before, but that doesn't answer my question. If it appears black, you mean it would appear black on infrared film?
No, I don't mean that. I mean that it exchanges radiation easily. A black body is something that radiates in all kinds of colors. That's all. In the white paint, titanium dioxide radiates and absorbs radiation in the infrared. If it can radiate in one wavelength, it can absorb in that wavelength. The universe has these funny rules. If you can, receive radiation in one wavelength, you can radiate it in the same wavelength. So titanium dioxide radiates and absorbs radiation in the infrared. But it gets very little, the top of your telescope gets very little radiation in the infrared from the night sky. But it radiates away, and the top side cools down. The bottom side stays warm by exchanging radiation with the ground. What? Well, the top of your telescope gets cold, and inside your tube you have cold air coming down like this across your field of view. The bottom stays warm, and you got warm air coming up across your field of view, and it wipes you out. When I had to look at an 18-inch F6 in Alberta, Canada, years ago, and he had a collar sticking out past the collar that holds the eyepiece and all that, and the diagonal. He had a collar sticking farther out, about nearly a foot, thin black stuff. 1/3 of his problem was there. Another third was in his black shroud, because that's not thermally opaque. The top side cools off, the bottom side stays warm, get cold air coming down, warm air coming up inside. So we had 1/3 of the problem in the collar out front, we took it off. Another third was in his shroud, we took it off. He has 1/3 left in the collar around the eyepiece and the collar and the box at the bottom. But you see, he thought it was a real lousy night with these big star images. But it wasn't a lousy night. The problem was with the telescope. Yes. Yes, when you look into the night sky or even the daytime sky, don't think that you're looking up. You will not understand it at all. As soon as you think that that direction is down, damn it all, you'll see how deep it is. You see, our genetic programming really keeps the pubic wall pulled over our eyes. It just tells you that you're perfectly safe if that direction is up. And if you think that direction is down, then you can see how deep it is. When you see somebody standing on a roof, it doesn't look so bad. But when you're on the roof, it looks bad. Looking up, it doesn't look so bad. That's just genetic programming. It's the same thing that makes the moon look so big when it's down on the horizon. Your genetic programming tells you that if it's on the horizon, it's very far away. It's very far away. The clouds are like that, the gulls are like that, the zeppelins are like that, the airplanes are like that, everything's like that except the sun and the moon. And your genetic programming tells you that since it's way, way over there on the horizon, it must be huge to look that big. And when it's over here, oh, it's so close, it must have shrunk. You know, we astronomers know exactly how big it is. Yes. nothing to say about nothing, except that it doesn't exist. The Big Bang people want to make the universe out of nothing, but they can't find any. I must be dismissed.
I have one question.
Go ahead.
I said I had a few.
I know you did.
All right, well,
I'm waiting.
all right. You sort of said that we were foolish because we thought, some of us had raised our hands, that the universe is infinite.
Yeah.
Okay.
The observable universe has a boundary.
I don't think it does. Let me explain to you why.
Go on.
It does.
Go on.
Maybe the observable universe
That's what I
absolutely
said.
has a boundary.
That's what I
But
said.
the universe is boundless.
That's just a guess, and it's not a good one.
Why isn't it a good one?
I'll tell you why. Because if the separation between the perceiver and the perceived is zero, your argument falls through.
I don't believe that at all.
I know you don't.
I really don't. I think that might be, you might be able to show that mathematically, but it certainly doesn't work in reality.
Now be careful. You're assuming more than you can chew.
How am I doing that?
Well, you see, you can ask questions from various standpoints, but you can't always answer the questions that are asked from various standpoints. Because if the questions are asked from the wrong standpoint, the answer can't come. There is that difficulty. But you see, if this universe is like a dream, it exists in the dreamer. If what exists is changeless, infinite, and undivided, and I feel perfectly sure that it is, that behind what we see is the changeless, the infinite, the undivided, otherwise you have no way to explain the physics. If behind what we see is not changeless, bicycles certainly wouldn't coast. And if it's not infinite, then the teeny little particles would not have to be electrical. And if it's not undivided, things would not have to fall together. So it seems to me that that's a fairly sure proposition, that what's behind what we see is changeless, infinite, and undivided. Now, if it's undivided, there's only one of us.
You said infinite.
I didn't say the universe is infinite. I said what we mistake for the universe is infinite. There's a hell of a difference.
Get mad at me.
I'll get mad at you.
See, I can't conceive of a finite universe.
That's your own problem. Whether you can conceive of it or not conceive of it tells you nothing about the universe. It tells you about your ability to conceive.
I think that the universe...
You can't think that it has a boundary out there, because then who painted the other side of the fence?
There isn't...
And you can't think that it doesn't have a boundary, because then it goes on forever and you can't handle that either.
I can handle it. It goes on forever.
All right. What? Oh, the dark matter. That's a good question. The dark matter is a very good question. What we know about star clusters is that when a cluster of stars forms from a cloud, something like 95% of the cloud gets blown away by the stellar winds. Now, I've asked this question to 3 professional astronomers within the last 12 years or so. 2 of them said that they thought that between 1% and 10% would make into the stars, and the rest would be blown away, but they didn't have a number on it. The last person I asked was at Caltech, and he right away said 95%, in some cases more, in some cases less, is blown away. So when a galaxy forms, we have the same problem. Something like 95% is going to be blown out of the galaxy, and it's going to be in the surrounding region, what I call the hovering layer. Now, it has to be ordinary matter, or it couldn't be blown out. Now, the Big Bang model has this spooky notion that most of the stuff in this universe responds to gravity only and not to electromagnetism or anything else. Responds only to gravity. If that were really the nature of the dark matter, it would all fall into the galaxies. We know it didn't fall into the galaxies. It's around the galaxies in my hovering layers. Yes?
Do you think the observable universe is the only universe, or is it possible as there is
When you're dreaming, you have only one dream to face. You don't have to face a plurality of dreams. I don't see any need for Everett's many worlds hypothesis. I don't see any need for that. But I cannot take the universe as actual. Actual would mean that it arises by action. It means that it arises by a process in physics. But all the processes in physics are covered by the conservation laws. And you can never get anything out that you didn't put in. And to hell with the Big Bang. There isn't any photon of light. Let me give it to you straight. In 1905, Einstein changed the geometry from 3D to 4D. And in his 4D geometry, space and time are a pair of opposites. And always for a photon, the total separation, the total space-time separation between the emission event and the absorption event is 0. Nobody ever saw a photon. Haven't you wondered about it? All we know about radiation is the emission event and the absorption event, and they have 0 separation in space-time. Space separations are not objective. Time separations are not objective. The only separation that's objective is space-time separation, and between the emission and absorption event for a single photon, it always goes to 0. When Einstein threw out the luminiferous ether, he should have had the decency to throw out the photons that swam in it. What? The speed of light is not the speed of anything. The speed of light is the ratio of space to time. 1 light year is equal to 1 year. 1 centimeter is equal to a jiffy. The photon doesn't have any mass. It doesn't exist. Nothing that doesn't exist has mass. All we know about radiation is the energy of the emission event and the energy of the absorption event, which are the same and have 0 separation in space-time. Now, this is not my idea. Now, let me tell you something. I'm unorthodox as a physicist. I'm unorthodox as an astronomer. I'm even unorthodox as a monastic, you see. But I'm not unorthodox about the equations of our physics. The academic community is unorthodox with respect to their own equations. I'm not unorthodox with respect to the equations, only with respect to their guts. Their guts, though, are the same as mine. They're full of shit. Yes. You see, this is not properly understood by everybody. Things coming toward you are blue shifted because of their speed. Going away, they're red shifted because of their speed. And if they come toward you, their mass is increased, and going away, their mass is decreased. But now, way back in the last century, in the winter of 1895-96, that's 100 years ago now, Swami Vivekananda, who represented Hinduism at the Parliament of Religions in 1893, met Nikola Tesla at Sarah Bernhardt's party in New York and asked him, can you show that what we call matter is just potential energy? Now, he did not get it shown, but Einstein's first wife, Mileva Einstein, was a good friend of Tesla. And she wrote Einstein's papers in 1905. And very probably she's the one who poked him to put in the appendix, in which E equals mc squared. Now, how did I get onto all that? Oh, so by 1905, you see, Einstein had written 2 papers. His relativity paper, from which he knew that things going away have their their mass redshifted away. Never mind redshifted, forget redshifted. Something going away from you is seen by you as being less massive. Something coming toward you is seen to be more massive, and he knew exactly how much. He also knew from his quantum mechanics paper in 1905 on the photoelectric effect that when things are going away, their radiation is redshifted, and when they're coming toward you, it's blue shifted. And he knew that the energy of the photons was related to the frequency. And he knew exactly how much they lose going away and how much they gain coming in. And he simply put those two things together. That if the radiation if the energy of the radiation goes down and the energy of the object goes down, it must be that the radiation and the energy are the same thing. Or the energy and the mass. I'm sorry, I used the wrong words. The energy of the radiation goes down and the mass of the object goes down. It's a very simple thing to notice that they're the same thing, because he has numbers on both of them. So in 1905, Einstein came out with two famous equations. First is that the geometry goes from 3D to 4D, and space and time come in as a pair of opposites. We see things away from us in space by the trick of seeing them backwards in time, the same as we do when we're asleep. And the other equation was that which we see as matter is just potential energy. Yes?
Yes, are you saying then that between the emission event and the absorption event, I can bring it back to astronomy, if we're looking at M31, there is no duration?
No, I didn't say that. I didn't say there's no time, and I didn't say there's no space. I said the total separation, the space-time separation is what goes to zero. Not the space separation, not the time separation. If you drive backwards out of your driveway for 5 miles and then come back in, you'll still be in the driveway. Yes.
Are you not indicating a paradox by saying that the particle or the object going away at the edge of the universe is getting less massive? What about the observer that would be at that particular point looking back at us? Would we not be getting less massive?
Everybody sees his own dream from his own position. And everybody sees this universe from his own position, which is always at the center. Ptolemy never had it so good. All the observers are at the center. Now, you see, even the Big Bang model has to have the particles recycling from the border. Even the Big Bang people can't get out of it. It has to do that. The only way you could get out of it is to put Heisenberg in the subjunctive. If I were at the border, you can't be at the border. So that's one thing that's another thing I don't understand about the Big Bang. This stuff has to recycle from the border.
What if the universe is radiating out like the sun radiates light and energy?
I just told you that the sun doesn't radiate light.
Well, you said there's a solar wind and it's losing mass and it's losing energy.
All right, yes. The particles are leaving.
They're leaving.
The particles leave at speeds lower than the speed of light, right.
They're leaving the sun.
That's right.
We'll never see the sun again in a relatively short period of time. Right? What if our universe is acting the same way?
In what way?
Its particles, its mass is leaving.
But the trouble is they can't get beyond the border.
Why can't they get beyond the border?
Do I have to go through this again? Because out by the border...
Gravity?
No. Listen up this time. When they approach the border, as seen by us,
I see by us is not good.
then stuff it. If the universe were actual, it would not be as seen by us. But if the universe is not actual, and it cannot be actual, then it's as seen by us.
You obviously don't believe in a big crunch at the end either, then?
No, I don't.
Okay.
And I don't believe there's an end either.
That's a way for the matter to get back from the edge, though, isn't it?
No, no. It's a continuous thing. A continuous thing. The density stays where it is.
Steady, steady. Yeah, very steady. Goes back
What?
Doesn't that come down to if man had evolved, would there be a universe?
Well, that's a problem that the quantum machinists have. They have to have a sentiency because always the observer gets mixed up in what he sees. But it doesn't have to be physicists, you see. I had a quarrel with some physicists in Michigan many years ago, and I said, yes, I know, you're very sophisticated beings. You know where down is. But if you really want to know where down is, you hang an insentient piece of lead on an insentient piece of string. And nobody opened his peeper. You see, matter is sentiency. All these things know where the earth is. If I drop my keys, I don't have them in my pocket. What do I have in my pocket? I have my salt bottle. If I drop this, you see, it knows exactly where the earth is. It knows exactly. No use telling me it doesn't know. Matter itself is sentient. If you didn't have a gravitational field, you would not notice the gravitational field of the earth. Gravitational fields are the only things that read gravitational fields. Electrical fields are the only things that read electrical fields. I've always wanted two pictures of myself. We have a great big scale here, and I stand on it. It reads 140 pounds. Then we turn it over, and I stand on it again, and it reads 140 pounds. And we'll show them both with the scales right side up. In one case, it's my weight and the gravitational field of the earth. In the other case, it's the earth and the gravitational field of me. If you didn't have a gravitational field, you wouldn't notice any anywhere else. Oh.
When does the book come out and when does the movie follow?
Well, you know, we did make a telescope making video, and I was hoping that the people who made the telescope making video would get this information out too. But I don't know whether they really will or not. But we're going to modify the telescope making video so we can put a barcode on it. There's not enough stuff about figuring the mirrors. But in case any of you do need any, I brought 5 with me. We make a 16-incher in the telescope making video. Yes. No, you're over there and I'm over here. However, you see, I have always thought, well, first I'm going to quote something. There's an old Indian scripture, in Sanskrit it says, when a man is asked who is there, he first says I, and then he gives some other name which he may have. We all have that nice name, I, and the question is whether there are 2 of it. It has not been shown in hard evidence in our physics that there are 2 of us. We have lots of soft evidence for the plurality of the observer, and we have no hard evidence. When you dream, in the dream you have a dream body, and you see many other dream bodies. When you wake up, you understand you were all of it. The physics says that it's that way now. The physicists don't say so. The equations say so. One thing I learned at the university was read equations. That I learned. You know, in the physics department, when you have a midterm, if you write a word, you get a 0. What they want is an equation, not a word. I must be dismissed. Oh, I get that.
Well, he can see it.
Different people have different things between their eyepiece and their brain. We had one lady at 5,000 feet in the Sierra when we had the 24-incher on the ring in '57, and I used to be able to see the central star. So I asked this lady, because I knew the pupils of her eyes were very big. Anyway, I asked her to go up and see if she could see the central star. Well, she says there are 2 inside and there are 2 in the nebulosity, and calls out the position angles.
Well, hell. By the way, a couple of years ago, I was visiting Patrick Moore.
Oh, good for
He
you.
showed me his Alpazima. He said, you know,
No, you shouldn't.
It's an Alpazima. He said, I know, but since you're American, you gotta do it.